Assalamualaikum and greetings to all. Today's topic is on triple integrals, which is the last section of this course. There are four sections in this chapter. The first section is on Cartesian coordinates. Second section is on cylindrical coordinates. Third is on spherical coordinates. And the last section is on some of the applications of triple integrals, which include moments and also center of mass of solids. Okay, let's proceed to section 6.1. Okay, so here we have triple integrals in Cartesian coordinates. Let's look at this theorem. Okay, so here we have let G be a solid where it contains set of points x, y, z, where x is between a and b, y is between c and d, and z is between k and l. And if we have a function f(x, y, z) which is continuous on solid G, then f(x, y, z) integrate over solid G. So here we have triple integrals. So here we have that dv. Okay, so triple integrals is going to be integration of a function over solid G. So here we have a solid G. So if our solid G consists of set of points x, y, z, where x is between a constant to a constant, y between a constant to a constant, and z between a constant to a constant, then our solid G will be a block or a cube like this, a cuboid. Okay, so this is our solid G, and we want to integrate our function f(x, y, z) over this solid G. Okay, so the iteration of dv here can either be dz, dy, dx, or combination of this. So the order of integrations in the iterated integral can be interchanged. So the above, so here, this is one of the iterations. It can be done in other 5 iterations. So it can be dz, dx, dy, dy, dx, dz. So altogether we have 6 combinations. So if your solid G is a cuboid, then the order of integration here is quite flexible. It can be done in 6 ways. Okay, so this is one of the order of integration. All right, and well, let me remind you, let me refresh your memory on double integral. Okay, so before we have in double integral we have a region. So here we have on an xy plane, let's say you have a region R. Okay, so this is our region R. So in double integral, what you have is you have a function f(x, y, z), and you want to integrate over this region. Okay, so this is double integral. And of course, if you only have dA over region R, that will give you area of region R. Okay, so that is double integral. And of course, in double integral we have 2 coordinates. One is Cartesian. So for Cartesian, then your f(x, y) dA over region R can be evaluated by evaluating the double integral using dy dx, okay, or f(x, y), the order can be done as dx and then dy. That is in Cartesian. Okay, but of course we have another coordinates in polar. So this is this is double integral. And just to refresh your memory before we go to triple integrals. Okay, and then in double integral we also have polar coordinates. Okay, for polar, we still have our function f(x, y) dA integrate over region R, but in polar, x will be changed to r cos theta, and y will be changed to r sin theta, and dA here will be changed to r dr d theta. Okay, so that is polar. So what you have in double integral is you're given a region. You're given a region R. Okay, and then you integrate a function over this region R. And if that function is happen to be 1, okay, then dA integrate over region R will give you area of region R. And dA here in Cartesian can be dy dx or dx dy. And in polar, dA is r dr d theta. So that is double integral. Okay, for triple integral, your integration would be over a solid G. Okay, so here this is the simplest solid, which is a cuboid. Okay, so in general we don't just have a cuboid, we have much more varieties of solids. So all in all, in triple integrals, that's ugly. Okay, in triple integrals we have x, y, z space. Okay, and then let's say you have a solid, probably a solid, maybe it looks like this. Okay, so this is your solid G. So it's in 3D, and now we want to integrate. So now you're given a function f, x, y, z, and you want to integrate over solid G. So that is basically what triple integral is. Okay, so and of course, similar to double integral, where in double integral, if our function is 1, then we get area. So similar to that, if our function fxy is 1, so if we only have dv over solid G, that will give you volume of solid G. Okay, and here now we're trying to learn. Okay, we're gonna learn, not trying, we're gonna learn what should dv be, what is the order of dv. So here in Cartesian, we have x, y, and z. So the order can be dx, dy, dz, dz, dy, dx, dy, dz, dx. So we have combination of that. So we have 6 combinations. So we want to know what order should we use. Okay, and of course, whoops. Okay, of course, in here, in our notes here, if your solid G is a cuboid, then the order of integration dv here can be done in 6 different ways. So one of them would be dz, dy, dx. Okay, so and then we have another 5 combinations. All right, and then of course, well, I've mentioned this before. We have a theorem. If our function fx, y, z here is 1, so we just have 1 integrate over solid G, that will give you volume of solid G. So similar to double integral, where area is dA integrate over region R. So in triple integrals, dV integrate over solid G will give you volume over solid. Okay, so now I'm going to show you how to arrange our dV. Which iteration should we use? Okay, so let's proceed. Okay, so here we have a more theorem here. So the first theorem is where your solid G is a cuboid. So order of integration does not matter. This is one of the 6 possible order of integrations. But if we have this kind of solid, okay, so here we have a solid G. So here this solid G is set of points x, y, z. So now you have points x, y, z. So it has x coordinate, y coordinate, and z coordinate. But here x, y is in region R, which is on the xy plane. Okay, so this is really the projection of your solid G onto the xy plane. So it's a projection of the solid on the xy plane. Okay, so if that is the case, and then here z is not from a constant to a constant, but you can see here it's from the lowest value for z is not a constant, but it's a function of x and y. So here this is the lower limit for z, because it's the one at the bottom. So that would be the lower limit for z. And here we have a surface, another surface. So this surface here is governed by this equation, which is also a function of x and y. So if this is the case, okay, so if this is the case, then the order of integration should be, well, you should integrate with respect to z first. Okay, you should integrate with respect to z first, and then the upper limit for z would be the top boundary, okay, the top surface of your solid. So the upper limit for z is the top surface of the solid, and the lower limit for z would be the bottom surface of the solid. Okay, and then once you replace z with upper and lower limits, which would be a function of x and y, then you're left with double integral. Okay, dA would be double integral. Then I know you're an expert in double integral now. Then you have to determine the order of your dA here. Is it dx dy or dy dx? Okay, so first thing is you need to integrate with respect to z first. So r on the xy plane here, okay, r on the xy plane would be the projection of g on the xy plane. It's like you're putting hang on, it's like you're putting a torchlight on top of the solid, like here you're putting a torchlight on the above the solid. Then r here would be the shadow of your solid on the xy plane. So we have r on the xy plane is the projection of your solid g on the xy plane. So the order of integration does matter. You need to integrate with respect to z first, and the upper limit for z would be the top surface, and the lower limit for z would be the bottom surface. So surface, it can be a function of x and y, or it can be a constant. Okay, all right, so that is one kind of solid. Okay, now let's look at another solid. Okay, so here we have a solid. Here we're gonna project our solid g. So it's like putting a torchlight on the right hand side. So here the projection of your solid g would be on the xz plane. Okay, then you need to integrate with respect to y first. Okay, so here in this solid, it has the right surface and the left surface. So the right surface, which is this surface here, this is the right surface, that would be the upper limit for y. Okay, it can be a function of x and z. Okay, so upper limit for y would be the right surface, and the lower limit for y would be the left surface. So here we have the left surface. It might be a function of x and z, or it might be a constant. Okay, so here we need to integrate with respect to y first, and then your dA here, it can be dz dx or dx dz. Okay, so that is how to integrate triple integrals when your solid has one right surface and one left surface. Before, your solid has one top surface and one bottom surface. Okay, all right, and then I think you can guess what the other yeah, this is another kind of solid. So here we have a solid G, where now you project your solid onto the YZ plane. So it's like putting a torchlight to the front, from the front. So when you do that, then the projection of your solid would fall on the YZ plane. So if you do that, then the order of integration should be, you should integrate with respect to x first. Okay, so for x, here we have the x coordinate. As you can see, it will be larger to the front, and then as you move backward, it would be smaller for x. So now the upper limit for x would be the front surface, the front surface. Okay, and the lower limit for x would be the back surface. Okay, once you integrate with respect to x, then you replace x with upper and lower limits, then you're left with double integral. So that double integral dA there can either be dy dz or dz dy. You choose. Okay, depends on the region. Okay, so that is how to determine the order of integration for your dv here. So if you're, again, let me say this again. So if your G is a cuboid, then order of integration does not matter. It can be done in 5 different ways. Okay, one of them is dz dy, dz dy dx. But if your solid has one top surface and one bottom surface, then you should integrate with respect to z first. So the upper limit for z would be the top surface, and the lower limit for z would be the bottom surface. Once you replace z with upper and lower limits, your dA here can either be dy dx or dx dy. But if you have this kind of solid, if your solid has one right surface and one left surface, then you should integrate with respect to y first. Okay, upper limit for y would be the right surface, lower limit for y would be the left surface. Okay, and if you have this kind of solid where it has one front surface and one back surface, you have to integrate with respect to x first. And then dA here can either be dy dz or dz dy. Okay, I will show you examples of this in our next video. Thank you.